What are my choices? If I have a linear system of two equations, what are the possibilities? Exponential or sinusoidal. Yeah. So you can either have oscillations or exponential. What did you guys find? Exponential, yeah. So you find exponential decay. And then we went on to say, supposing the clearance rate, C, is bigger than mu, right, then you can essentially say that the C will go away, the e to the minus ct terms will go to 0 quickly, and you're left with the mu term. But then I made this, there's a cryptic comment in here that says, show that v of t decays exponentially after a short phase of slower than exponential decay. And some people ask me about that, and I think it's worth just to draw on the board a little bit for that one. Okay, so let's just think about what v of t should look like in this model. Okay, so where are we first of all, where are we starting? We're starting at the steady state, whatever the steady state is. So this is VSS, yeah? We're starting at the steady state. Okay, now, without calculating, what is the derivative of the curve here, of the V curve? 0. So why is it 0? Because it's a steady state. Okay, now, so we turn on the drug. Okay, so we agree that it's 0, but this is also where we turn on the drug. So initially it's 0, but then how long will it be 0 for? Not very long at all, right? Okay, so what is happening is we turn on the drug, but we still have these cells which were already infected, and they're just sitting there pumping the virus, right? So this is the virus, yeah? Okay, we could also plot the cells. What does this look like? This is exponential decay, right? Okay, so this is exponential decay. This is TSS stuff. Okay. Okay, so we have exponential decay of the cells, but the cells, initially, there's a lot of cells still present, and those cells are still producing virus, right? So it doesn't drop immediately, it doesn't drop exponentially, yeah? We should agree on that. And in fact, we know that the derivative is 0, yeah? But we also know that after a long time, we see exponential decay with rate c, yeah? So we sort of know that we should be finding exponential decay over here. So how can I have a flat curve here and an exponential decay curve here? There has to be something like this, right? Yeah? Okay, so I plotted this on linear axes because it's easier to do linear, and this is exponential decay. If I'm plotting this on log axes, okay, if I was plotting this on log axes, this part, the exponential decay part would be a straight line, right? So essentially it would look like that. So that's supposed to be a straight line. Yeah? What do we have here? We have a transition, yeah? We have a transition from more or less flat to exponential decay. And that's what I meant by a phase of slower than exponential decay. So it's decaying slowly as the old cells are killed off. And now we're not getting any new cells, so now we just see pure clearance of whatever virus is left over. Okay? So that's what I meant by that comment. Yeah? And you don't have to calculate to understand how the plot will work. This is really supposed to be a straight line. I'm not happy about that. I'm going to draw it again. Okay. See if I can draw a straight line. That's better. Okay? And the slope of this line, yeah? The slope of this line is c. Yeah? Is c, because that's the long-term rate of decay. No. You can't. Why are you all nodding? It's not c. What is it? It's mu. It's mu. Yeah. I wrote the wrong thing. Yeah. It's mu. Yeah. Okay. Okay, good. All right. And because that's mu, right, very approximately, if we're seeing a decay, if this is a factor of 100, okay, and this is 14 days, yeah, and this is 14 days, yeah, so it's a factor of 100, yeah, that's exponential decay by a factor of 100, right? So initially, so if we just say approximately, sorry, V is approximately V of 0, or VSS, e to the minus 14t. So just ignoring this bit, going straight to this bit, Okay, so just ignoring this initial part and going directly to this part. Okay. So why did I put 14 there? That should be mu, my bad. Yeah? Well, yeah, hold on, I'm not quite there yet. This is the general equation that I was trying to, I did both, that was the problem. All right, so V0 equals VSS, and V14 equals VSS over 100, right? Okay, so e to the minus 14 mu equals 1 over 100. And so that I can solve for mu, and I get mu is equal to, did anyone do it numerically? Sorry? 7e?
So I've got like between 0.16 and 0.33, depending on whether you use 1/10 or 1/1.
Yeah, so 0.16, no, this would be 0.33 because it's 100. So mu is 0.33. What are the units?
Per day.
Per days. Yeah, so 1 over days. Yeah, so how long does an infected cell live during HIV infection? How long does the cell live?
3 days.
Roughly speaking, 3 days. Yeah, 1 over that rate is the lifetime. So roughly speaking, an infected T cell lives for about a few days. Yeah. Make sense? Yeah, so we can learn a lot, right? Okay. All right. For parts C, and D and E, I'm going to skip over those. Essentially, the idea was that as the drug becomes more effective, you should get a steeper decline. Okay, that's essentially, if you have a slightly less effective drug, you don't get the full decline at quite the same rate. Okay, all right. Okay, good. Any questions? Yes.
Comment.
No, the long-term slope here is mu. Okay, so let's just remember what was the solution of the problem. Okay, so if you solve the following problem, so dt star dt equals minus mu t star, right? Agreed? That was the equation we should solve because we set k equal to 0 because the drug is 100% effective, right? Oh, hold on. Okay, so t star equals t star SS, right? Yeah? E to the minus mu t. Okay? Agreed? Okay, now what's the V equation? dV dt equals to P times T star okay? Now we solve this. Okay? Now, I don't want to solve it explicitly because almost everybody actually solved it correctly after some time, yeah? But if you solve this, you get V is equal to e to the minus ct times some constants plus e to the minus mu t times some constants. Right? Agreed? Okay, so which is bigger, C or mu? C is bigger, so this exponential decay will go away. So if this goes away after a little bit of time, you're left with this. So after a little bit of time, the decay should be at rate mu, okay? Roughly speaking. I mean, it's not exactly correct, but we're trying to get the picture here, right? Yeah.
Viruses get it.
Yeah, so okay, that's a good
That was the question really, what defines an infected
Yeah,
cell?
yeah, I understand what you mean. So it's true, the viruses can still get into the cells. That's true. However, I think the key thing is that when you apply this drug, you still have a population. If the drug was setting P equal to 0, then basically the virus would just decay exponentially. That would be it, right? And you would still have infected cells, and they would die, presumably, but they wouldn't be producing any viruses. Okay, so there's a distinction there from the reverse transcriptase inhibitor, which essentially prevents productive infection of cells, okay? So then we see this behavior where the cells which are already infected continue to produce virus at more or less the same rate for kind of a while until they die, and then we transition to a cell death rate controlled decline, okay? But I think it's a good question. So the question that was brought up is, how do we define an infected cell? So actually a lot of models, if you're being very precise with your modeling, they introduce in between uninfected and infected they introduce kind of an exposed class, if you like, in the language of epidemiology, which are cells which are infected but have yet to produce any virus. So there's many models out there where there's an intermediate class here. So there are cells here called T something, what should we call it? You could say that they're exposed, I guess, yeah. So the virus has already gone in, but it takes some time for them to become productive cells, okay? So we can write a model like that quite simply. Or you can even put in more steps. You can have different steps inside the infected cells and structure it like that. Yeah, so it's an interesting thing to do. And in fact, we'll see a little bit of that later on. Okay, so it's time to move on now. So this was supposed to be the safety, okay? This was the safety of the ship, okay? And now the ship is going to sink and we're all going to get on the life raft together and we're going to learn some things about stochastic models. Okay, so from my understanding, Professor Bard last week was talking a lot about differential equation models. Yeah, okay. And so we're going to move a little bit away from differential equation models for a while, okay? So this is going to be exciting. So did anyone here study branching process before? Okay, it's going to be very exciting, okay? So we're going to try to do something of this. So let's move on now. I'll be around at lunchtime if you want to talk about problem 2 or the latter parts of problem 1, okay? All right. Introduction to branching process models. Okay, so it's bolded, so I guess that means we have to do it now. Okay. So why would you want to use a stochastic model? Okay. So differential equation models are perfectly good tools when you have a lot of things going on. Okay? So when you have many players, okay, when there are many events happening, okay, so that you have lots of viruses, you have lots of cells, it's basically impossible to count because there's so many. So you look instead at concentrations, yeah, cells per human, viruses per human, and you kind of have a continuum approximation. So in a differential equation model, you can have half an infected cell, right? But T and T star and V, they're all continuous variables, right? In reality, these things are discrete. We should count them. But in this model, we make an approximation. There are so many of them that we don't really care. You know, we just kind of average them out. So stochastic effects are very important when numbers are small, okay? So if you have only a few cells, yeah, or only a few viruses, or if the events occur very rarely, yeah, so there are big time gaps in between the events that you're interested in. So one example is panda reproduction. So pandas, you know what pandas are, right? Yeah, pandas, yeah, they rarely reproduce. So it's very important to understand that that is not a differential equation process. The world panda population should not be modeled with differential equations. On the other hand, the world population of bacteria, yeah, or even the population of bacteria in a small glass, that would be fine. We can model that with differential equations all we want, right? Another example is the following. It's a little more abstract maybe, but so you know a casino where you go to gamble, right? So if I take my paycheck and I go to the casino and I gamble, I'm really interested in the stochastic effects, yeah, the big fluctuations, because I can end up with no money, or I could end up with, fairly unlikely, I could end up with a lot of money, but it could happen, yeah. On the other hand, the guy who owns the casino is much more interested in differential equations, right? Because there's a lot of suckers like me who come to the casino and bet our paychecks, right? And he can average these things out, yeah? But he's also interested in large fluctuations, but you get the idea, right? There's different perspectives. Okay, so if you have small numbers of things, you should have a model which reflects their discrete nature and reflects the fact that the events don't always happen just all the time. They can happen infrequently. So I want to describe, so what examples might we have in within-host virus infection? So specifically looking at HIV. Okay, so the first bullet point is important. It's actually quite difficult to become infected with HIV on a single event basis, okay? So if you just sort of have sex casually, then most likely there's a less than 1% chance of transmission, Now, those are the general estimates. It's actually quite rare. The government tells you to be very, very careful because they're looking at the whole population. But from an individual point of view, it's actually quite rare. Okay? Even if you receive a blood transfusion from an infected donor, there's actually some probability that you don't get infected, which is really shocking, but apparently it's true. This is from the early days. Also, most developed infections, or many developed infections anyway, show a single founder, which means that all the viruses in a patient's body are descended from one virus. Okay? So this actually means that infection is actually kind of a rare event. Right? It's kind of an unusual event. So if basically what they do is they sample virus from the blood, they do a phylogenetic tree, and they find that it comes back to a single root. Okay? So they find the family tree, and the most likely scenario is a single founder strain. Okay? All right. So initial infection, therefore, is actually a stochastic process. Right? There's an element of probability there. It shouldn't be modeled with differential equations. Okay. In treated infection, too, when you're being successfully treated, your viral load is very low. Okay? However, this is a patient who was on treatment for 5 years, and they were regularly tested. Now, the 0 here doesn't mean really 0. What it means is undetectable, okay? But it's plotted as a 0. Okay, so these are all undetectable, undetectable, undetectable. So he kept going to his doctor and being tested, all these undetectables, and then one day he had a detectable viral load. But then the next time it was undetectable. All these undetectables, and then finally a detectable viral load. Okay? So there's some sort of stochastic process. It appears to be some sort of effect. From our point of view, it's a random process. Yeah? That you have these unusual events that are happening to a few patients. This patient, patient 25, had one viral. These are called viral blips. They had a viral blip there. So they had a measurement, and the next time there was no virus.
Sorry, are these patients who you would say are infected patients that are known to be infected?
They're definitely infected because they're on treatment. So that they were definitively infected.
So I would have thought that this picture could arise from just the stochasticity in the diagnostic.
Yeah, that can happen too.
You could get a blip.
Yes, that can happen. And the thing is the threshold of detection is around 50, so actually blips are up. But the fact that, if we just take this data at face value, and there's some reason to believe that we should, then you can definitely say that these larger ones are true blips. This is not a diagnostic test error. I'd be surprised if it is, because it's fourfold above the detection floor. So it could be that the viral load is actually fluctuating around 25 or 30 here, right? And occasionally we're picking it up. But again, stochastic thing, right? And you could incorporate the reliability of the test into your model too, if you wanted to. Yeah. Yeah. Okay. So that's a good question, but few, right? It should be few. Yeah. Yeah, there's probably an answer to that question, but I don't know what it is. Yeah, yeah. At some point, right? So as you gradually increase the viral load, at some point you don't need to worry about stochastic effects anymore. Yeah. So I don't know, a few hundred infected cells probably. Okay. Yeah. I wish I could give you a better answer. I think there is one. I just don't know what it is. Yeah. Okay. All right. So let's just look at this in a different way. Okay, so let's just make this very simple. Okay, we'll go away from the whole virus and cell business, and we'll just have cells. Okay, so now you can even imagine just bacteria living in a dish. Okay, just cells. Okay, so you have a cell, and the cells reproduce at a rate B, and they die at a rate D. Okay, so we have B, the birth rate, and D, the death rate. So how would we model this with a differential equation? So if n is the number of cells, we would write down dn dt equals the number of births. So the rate of change of the number of cells is going to be the number of births, the rate of births, minus the rate of deaths. Agreed? I can solve that. Yeah? Okay, and what I get is if B is bigger than D, I get exponential growth. If D is bigger than B, I get exponential decay. And I have absolutely no way of saying pandas have a 98% chance of extinction. It's impossible in this model, right? For one thing, nothing can ever go extinct. This never goes to zero, right? It never hits zero. Yeah? So what I'm going to show you guys in the next few hours of class time and this afternoon in the computer lab is a method for dealing with this kind of problem, okay? For dealing with essentially the simplest forms of stochastic modeling, okay, which can cope with individuals as opposed to concentrations, all right, and discrete events. Okay, so we're going to do this thing, it's going to be called branching process, and it's going to allow us to say things like, this population has a 98% chance of extinction. Okay? All right. Okay, so to do that, what we have to do is we have to go to this probabilistic interpretation of the events. Okay? So I'm going to write on the board a little bit. Okay, so let's just think about it. Suppose that we have, in our cell population, suppose that we have 3 cells. There are 3 cells to begin with. Okay, so we're starting with 3 bacterium. Okay, so what can happen? We have 3 bacterium, what can happen to change that? A cell could die. So he's a pessimist, right? He said a cell can die, okay? So he's feeling pessimistic. So what rate does that happen at? The death rate, you know? D. Actually 3D. The rate of death to go to 2 cells, yeah? This rate, there's some, I wrote it as D there. Technically it's 3D, because there's 3 cells and each of them could die, yeah? So 3D. You can write it whichever way you want. It depends on how you think. Yeah? Okay. All right, what else can happen? Come on, optimistic person. A birth. Yeah, we should all celebrate, right? Okay, so you can also have a birth. Okay? So at rate 3b. Yeah? And then we will have 4 bacteria, 4 cells. Yeah? And I can now obviously put in all the other arrows. So this arrow here should be 4D, and this arrow here should be 2B. Yeah? These are the rates that these things happen at. And this guy, one of these guys can die. And, oh no. Oh no. You see there's something a little bit unsymmetrical there? 0, yeah, extinction is forever, right? Yeah? Once you're extinct, that's it, you can't have any more births. Yeah? There is a thing called a birth-death immigration model where you also have new cells coming in, and that's an interesting model, but we're not going to do that, okay? All right, and ... right? Okay. So those are the things that can happen, but they're random events, right? So we can say there's a rate at which this event happens, but we don't know. Remember I said we're going to start at 3. We don't know what's going to happen first. Is somebody going to die? Or is somebody going to be born? Now, what we can say is what's the probability of one event happening first or the other event happening first, right? And we can also say how long will it take until that happens? Because if the rates B or D are fast, then you could rapidly accumulate events. And if the rates are slow, then maybe it will take years or even longer, yeah? If this is a population of trees, could take hundreds of years, yeah? If there's a population of bacteria, it takes a few hours, yeah? Okay. All right. Okay. There are a few assumptions. We're assuming a constant rate. Okay, we're assuming constant rates. What does that mean? Constant rate means, okay, the probability of having a birth is constant. Okay, it never changes. Okay, so even if it was a long time, so even if I wait years and years for my new birth event to happen, the probability of it happening in the next time step, the next day, is exactly the same. It doesn't get more probable. Yeah? It happens at a constant rate of events. Okay, so everything is and also everything is independent. So these are the assumptions that underlie the birth-death process that I'm describing. Everything is independent, yeah? So and also you can't have two births at the same time, or a birth and death at the same time, or anything like that. You can only have one event at a time. Okay, any questions about the sort of basic idea of the model?
So you can directly add 4 to 0, this delta that only happening for no happening.
Yeah, basically, every time you're here, you're essentially rolling a dice. You know, as if you're playing like a game, yeah? Yeah, you're rolling a dice and one thing will happen or the other. Yeah? Make sense? Everybody good? Okay. All right. So it's different than differential equations. We can agree on that, right? Yeah. Okay. Yeah.
Are we assuming, so essentially we're assuming b plus d equals 1?
No.
That's
No. B, so that's a great question. He just asked, does b plus d equals 1?
Plus 3b plus 3d should, something is always happening.
No, we're not making any assumptions. These are rates. Okay, so these are, you can, if you move to a situation where you have discrete time steps, then like all the probabilities of something happening plus the probability of nothing happening should add up to 1. Okay, but these are rates, so these can happen at any moment. This is a continuous time process. Okay, it's a continuous time process. Yeah. Days or weeks or minutes. No, it's not constant. This is a continuous time. I'm doing a continuous time process here, okay? So these are rates. The 4D is not the probability of a death. It's the rate at which the death events happen currently is 4D, okay? And then they will happen when they want, according to that rate. If D is a big number, the deaths will happen more frequently. If D is a small number, take longer between the deaths, okay? No, you've got independent cells. They're living, one is here and one is here, and they had to decide independently what's going to happen. So either this one makes a birth or this one makes a birth. It's an or, not an and.
Then there is another possibility that there's time.
Yeah, we don't allow that. There is a single event. So as I take delta t goes to 0, if you want to do it, if you want to play that way, as I take delta t to 0, a single event happens. Okay? Okay?
Surely that means that birth and death events are not independent because one can block the other.
If you had finite delta t's, if we worked in days and I counted the births in a day and the deaths in a day, yeah, I agree, because then I would only be allowing. But because this is a continuous time process, I'm taking the limit as my time unit goes to 0. So eventually, you know, even if it's birth, death, they're still separate. Death, birth, you know, yeah, I'm taking my time step is effectively small enough that it doesn't happen. Or it becomes very rare, extremely, so rare that we don't think about it anymore. No. No, we don't allow that, okay? Only one, it can go death, death, as fast as you want. You can talk faster than me, death, death, yeah, okay? But yeah, but there is some limit that we can only have one event that happens at a time, okay?
So can we just say death, the D represents characteristics of time?
1 over D is the average distance between death events for an individual. That makes sense. Yeah. That's how I would say it. Yeah. Okay. All right. Now, we start off at 3, right? And we can, with some probability, increase and with some probability decrease. So even though we start at 3, after some time, what we actually have is a probability that we are at 4, and a probability we're at 3, and a probability we're at 2, and even a probability that we had a lot of deaths, right? Yeah? So we can no longer talk about the system has this many cells. What we talk about instead is what is the distribution of probabilities across the cells. Yeah? So what is the probability of still having 3 cells? Okay? All right. So this is an important thing. I'm going to write down what it is. So P sub n0 of t. Okay, so this is going to be a basic object for a while. Okay, this is the probability. I'll write it too. I'm going to say it first. The probability that at time t we have n cells given that we started with n0 cells. Okay, so we're going to start with, so if n0 is equal to 3, like I said, this will be 3 all the time, and then we just have the probability we have n cells, given that we started with 3 cells. Okay, so the probability of having n cells, given that we started with n0 at time t. Okay, so this is the probability that there are n cells at time t, okay, given that we started with n0 cells at t equals 0. Okay, so just for simplicity, we'll always start at t equals 0. Okay, great. Okay, so that makes sense. So we automatically know that if we add all of these guys together, so if we sum over n, it has to be equal to 1. Okay? Okay. All right. Great. Okay, so now what we're going to try to do is we're going to try to write down a differential equation for the p's. Okay, we're going to try to write down a differential equation for the p's then. Okay, actually, first of all, we're going to look at some simulations. Sorry. So here are some simulations. So here, we start with, it looks like we start with 1 cell, and the birth rate is 3 per day, and the death rate is 2 per day. So on the whole, birth is better than death, right? So on the whole, the population should increase. And there are some simulations. And you see on the whole, those simulations are increasing. Except for, I said I made 10. What happened to the other 7? They went extinct. Yeah, they went extinct. Yeah, some people fell off the bus, right? So back down here somewhere, some of them went extinct. And we're just left with these 3 that survived. It's kind of interesting, right?
Dangerous to have only 1 cell.
Very dangerous. If you're down to, I mean, yeah, cells, pandas are a little different, and I'll explain to you later on, but you need 2 pandas. Okay? All right. But yeah. So yeah, you cannot go, if you go low, it's dangerous. You're at risk of extinction, right? Yeah. Okay. If I do 100 simulations, you can see that not all the simulations look the same, right? So this process, the size of the population as a function of time, is, first of all, it's not monotonic. Yeah, it doesn't always increase, even though the birth is better than the death. Secondly, there seems to be a risk of extinction. Like you could accidentally die, have a few cells die and go down to 0, and then you're stuck, right? Yeah? And then the other thing is, there's quite a spread between the biggest population and the smallest population, even for the ones that don't seem to go extinct. Yeah? Okay. All right. And if I zoom in, so I'm zooming in here on the early times, what you can see is, look, there's a blue one here that was doing quite well at this point, yeah? But then a bunch of death events happened, and this blue one went extinct, yeah? So there's always some risk of going extinct, right? It may be a low probability, but there's always some risk of going extinct, okay? Or even this green one. This green one, you can see, was having difficulty deciding if it was going to increase or not, yeah? And then finally, the individuals decided they'd had enough. They just gave up. Okay. All right. And in fact, we can count how many are extinct or alive after 100 minutes, or 100 days, rather. So after 100 days, 62 of these guys were left, and 38 of them were dead. Okay? So roughly speaking, 2/3. Well, the death rate is 2, and the birth rate is 3. And I just want to say, roughly speaking, 2/3 of them went extinct. But I'll leave you to figure out what you think about that statement. Okay? Anyway. And if I do 1,000 simulations, roughly speaking, 2/3 of them survived. Okay? We get a lot of spread, though, a lot of spread. And if I do 10,000 simulations, it actually doesn't render very quickly. So I just tell you that, oh no, that's the wrong thing. That 6,700 of them went extinct and 2/3 of them survived. Sorry, 1/3 of them survived. Okay, so I already told you about this. Yeah.
So there are so many species kind of things. So they are also having birth rate and death rate. It means some species will die automatically.
Yeah, yeah. If you're a new species, there's a pretty high probability, even if you're like Superman, that you'll just die, right? No, imagine you have like, I don't know, some mutation happens in a population. That mutation there's a pretty good chance it's just going to die, no matter how fit it is, right? I mean, well, if it's extremely fit, I guess theoretically it won't die, but if the birth rate for the new one is just a little bit higher than the rest, might not work out, right? Might not work out. Is that what you were asking about? Yeah. So it's very risky being a single individual. Okay, so I already told you, okay, so this is my probability. Okay, this is the fundamental object we're going to work with, is this probability. Okay, and we can also talk then about the extinction time. So what's the probability that you're extinct by time t? Okay, so this is like a distribution of times to extinction. Okay, all right, so how do the probabilities change in time? So if you were following the slides and not listening to what I was saying on the board, then you should probably agree with this statement. Okay, so the probability that you have n cells, delta t after some previous time, okay? So we have time starts off at 0, we go up to t, and we want to know what happens by delta t, more time, okay? So the probability of having n cells, delta t later after some other time, yeah, is equal to, okay, so how can you get to n? There are four ways you can be in n, yeah? Yeah? You can there are 3 ways you can be in n. Sorry, my bad, 3 ways. There are 3 ways you can be in n. Okay. You can have a birth. Oh, I got it wrong. So we'll start with the death. You can have a death. So you could have been at n+1 cells here, and then you could have a death. So how does that happen? Death times the so one of the n+1 cells died, okay, in time delta t, times the probability that you were at time t you had n+1 cells. Make sense? So this is the death probability. So what we're doing is we're moving the probability from Pn+1 to Pn. Sorry, this is Pn, and some probability is moving here from Pn+1. And it happens according to the death rate. Okay. Alternatively, you could have been at n-1 just beforehand, and you can have a birth happen. So the number of births that will happen is Bn-1 times delta t. Right? That's the rate at which the births will happen. Okay? Again, I'm assuming that you can't have 2 events within delta t. I picked delta t so small that you can only have 1 event. And then the third way that you can have n cells now is if nothing happened. You had n cells just before, and now nothing happened, so you still have n cells. So the probability nothing happened is 1 minus the probability there was a death and the probability there was a birth, times the probability you're already there. Okay? Oh, whoops, sorry, my bad. That bracket's in the wrong place. Sorry. The bracket shouldn't be at the end there, it should be just after the delta t there, okay? So do you agree with these rules for how the probabilities move around? I mean, there's a little bit of hand-waving going on, right? But if you look carefully at these rules, I think you can convince yourself that this is how it should work. Okay, so does anybody have any idea at all what I'm going to do next? Yeah. What I'm going to do is I'm going to try to form a derivative on the left side. So conveniently, I'm sorry about this bracket. That bracket should be there. Okay. Conveniently, I have a 1 times Pnn0 here. So I can subtract that onto this side. And then I have lots of delta t's. I can divide by delta t. Okay, so if I make those 2 steps, okay, then just so simply rearranging that equation, I get this equation. And now we recognize this thing as looking a lot like a derivative. We take the limit, delta t goes to 0, okay? And now we have what's often called the master equation for this system. Okay, so this is called the chemical master equation or the forward Kolmogorov equation, okay? So this is the rate of change. This is a differential equation. Actually, it's a system of differential equations. So for each p sub n, for each one of those p sub n's, for all the values of n, all the possible population sizes, I have an equation like this. And so they're all linked together. Make sense? Does that make sense? Okay, so now what we do is we go home and we solve an infinite system of differential equations, and then we have our dinner, right? Okay, there's infinitely many equations here, right? N naught is just the initial condition. Yeah, the n here, but there's infinitely many possible n's. N goes from 0 up to infinity, yeah? Yeah, so every possible population size has an equation like this, yeah? But this tells me how the probabilities of being in each one change from time to time. Okay, so this is now solvable, right? This is solvable. Okay, so it's time to do some work.